This is problem 219 in the Smith Van Ness 8th edition textbook. We have liquid water at 180 degrees C, 1002.7 kilopascals, has an internal energy of 762 kilojoules per kilogram and a specific volume of 1.128 centimeters cubed per gram. We're asked to find, first of all, what is its enthalpy? And then secondly, we're told that the liquid water is brought to a vapor state at 300 degrees C and 1500 kilopascals, where its internal energy is 2784.4 kilojoules per kilogram and a specific volume of 169.7 centimeters cubed per gram. And we want to calculate the delta U and delta H for that process. So I'm going to be working this in MathCAD. First thing I do when I open my file is I notice that the units, at least for my version of MathCAD, are going to be using kilojoules and kilopascals, and so I have to define them for this problem. Now, as far as solving this problem, we want to know what the enthalpy is for this water, liquid water. And so the first thing we should do is think about, well, what is the definition of enthalpy? The nice thing is we are given the internal energy and the volume, the specific volume. And so you should be able to realize that we can just use a definition of enthalpy. Enthalpy is defined as the internal energy plus the pressure times the volume. And so here everything's on a per mass basis. We know what U is, that's given to us as 762. We know what pressure is, that's 1002.7 kilopascals, and we know what the specific volume is. And so to do that problem, it's just a simple application of this definition. We enter our U1, we enter V1, and again notice MathCAD grams is GM because G by itself is the acceleration due to gravity. We enter the pressure, we define the equation for enthalpy, and then we get our final answer of 763.1 kilojoules per kilogram. Notice the nice thing about MathCAD is that it does the units for us. It does a conversion from centimeters cubed per gram to meters cubed per kilogram, and then it also does the unit conversion of kilopascals to, say, a Newton or kilogram meter per second squared per meter squared. And so the answer is given to us right there. For the second state, we want to calculate second part, we want to calculate the delta U and delta H for taking this liquid water and changing it into water vapor. And so we can do the same kind of calculation. First thing I'll do, we know what the internal energy is, what the specific volume is, we know what the pressure is, so we can just apply that definition of enthalpy again. H2 is equal to U2 plus P2 V2. Again, the nice thing about MathCAD is it takes care of our units for us, but you would do the same unit conversions if you had to do this by hand. And so we get an enthalpy for the second state of 3039 kilojoules per kilogram. For the overall process, we then calculate H2 minus H1. So H2 minus H1 is 2276 kilojoules per kilogram. We can then calculate delta U. That is 2022 kilojoules per kilogram. And then finally, just a couple notes. As I mentioned, we just do these calculations using the definition of enthalpy. And as I mentioned, if you're doing it by hand, make sure you do your unit conversions correctly. The other thing that I wanted to bring up, this is a phase change. And remember earlier in the semester I had mentioned, be very careful whenever you see a phase change that you are taking into account the latent heat of vaporization or the internal energy change due to vaporization. Do we need to do anything special for this problem because of that? The answer is no. And the reason is because these internal energies, this internal energy and the specific volume that we're given, we're already account for that phase change that's occurring. Notice this is a huge increase in specific volume, and that's what you get when you have a phase change. And we have a huge increase in the internal energy. If you were to actually calculate the latent heat of vaporization, you would find that most of this delta U is involved in the in the phase change. So in this case, we do not need to go look up any latent heats of vaporization or anything like that, because the information that was given to us already accounts for that phase change.